Last time, in the previous times, we reviewed solid mechanics, mostly elastic mechanics, because metals, they usually does not permanently deform in our machine. If we have permanent deformation, it's considered as a failed product, failed system, failed part. So we are mainly focusing on safe design. But we need to know how safe it is. Okay? And today, we are going to talk more about whether a design is safe, whether a component is safe. And we are focusing on static loading conditions. Okay, which means the load is there. Static means the load condition is there, but it do not change with time. Oh, by the way, whenever you see me do this, this is with. And when you see this, this is without. Okay? And when you see this, this is because. What else? Yeah. Okay. This is with, this is without, this is because. If you see those. Okay, so when you say static, that means there's some kind of low condition, but it doesn't change with time. So if I have a beam right here, this time I bring something. So if I apply a load right here, the load is always there. I don't take it away or I don't increase it, it's always there. And as time goes by, the force is always there. So let's see when a material is under some static loading, let's see if the material will fail. Okay? So in this kind of problem, what we are worried about is yielding. We worry about yielding because for materials, stress and strain relationship, we are mainly focusing on this linear region or the so-called elastic region. And when we pass the yielding point, we have nonlinear deformation and it doesn't recover back. So we are focusing on here. So when it's under a static load, the first possible failure this could face is the yielding. If yielding happens, it's a failed part. Okay, so for static loading, we worry about yielding. To tell you more about the other cases, for you to, let me explain more before I move on to the next slide. What if the load is not static? What if it's a dynamic load? For example, I'm applying a force and I sometimes take it off and then apply a force. So I'm doing this for 10,000 times, 100,000 times, or even more, 1,000,000 times. Maybe the force that I apply doesn't cause yielding. But for all kinds of material, especially for metal, if you do this, if you apply a force for a long time or for a long amount of times, multiple times, if you do that, the strength of the material becomes weakened. It is weakened. So originally, it was able to handle this kind of loading. But after a long time of being applied with some load, the strength become lower. So we will focus on that in the future. But to compare, let's just briefly introduce what's going to happen for dynamic loading. Your yielding strength will actually drop. Okay, it drops. So if this drops, we sometimes doesn't call it yielding strength anymore because it will be confusing. So we give that strength a different name. Okay, a different name. We call that endurance limit. So endurance limit is a different name to represent the yielding strength, and it's related to how much times you apply the force onto the material. So if this is like a fresh material and you have never applied any force onto it, it's like it still has the original yielding strength, like a 100% fresh, just freshly made. So based on what we know about the material, it should have some level of yielding strength. For that kind of workpiece, in fact, it is strong as you expect. But if the same material being applied some force for a long amount, a huge amount of times, that strength drops. Okay, so when that strength drops, we will give that number a different name, endurance limit. Okay, and usually for 1,000,000 times of we call dynamic loading or dynamic loading cycles. How about this? Loading cycles. For this huge amount of loading cycles, what's going to happen is the endurance limit will drop to a certain level. Could be as low as half of your ultimate tensile strength. Okay, so this is just like a brief idea of what's going to happen. If you have cyclic loading, or sometimes we call fluctuating or cyclic, or just dynamic, okay? All kinds of loading. Dynamic means it's not static, then it's dynamic, right? Fluctuating is like it's moving up and down, and you cannot describe how it's changing, fluctuating. Fluctuating is like vibrating, okay? Okay, 浮动, okay. Cyclic is like there's a cycle. So there's a very constant cycle following some kind of pattern. Okay, for example, in a machine, like a machine tool, like a 工具机 machine tool, inside there is a workpiece. The only motion a cylinder can move inside a machine tool is to spin like this, is to rotate. So this machine can only rotate, and the kind of loading this cylinder can handle probably is within certain pattern. So usually, if there's a loading from top to bottom, and it's always rotating, then it's under a cyclic loading. It's, for example, if I draw a cross right here, and if I apply the load from the top side, where I have the cross, and when it spins to the bottom, when the cross is at the bottom, then the cross is under a different kind of load. When the cross was on the top, the top side of the cylinder is under tensile strength. Tensile, right? Pulling. But when this rotates to the bottom, the bottom side is under compression. So think about the cross. When it's on the top, it's being pulled. When it rotates to the bottom, it's being compressed. So if the load is right there all the time, and if the cylinder is always rotating, then focus on the cross. It's being pulled, compressed, pulled, compressed. It's a cyclic loading. It's not good for the rod because that cross is under a cyclic loading because it's being pulled and pressed. So if I have a certain load and I spin this cylinder for 10 to the power of 6 times, then that particular point is under a loading cycle, being pulled, being pressed, pull, press, pull, press, 10 to the power of 6 times. After that, the strength of this material will drop a little bit. Okay, so we know, before I start, I need you to understand, if we have static loading, we're only afraid of yielding. But if we have dynamic loading, because the strength will drop, so the material can fail in a different way. So we call this fatigue. Okay, so what is the Chinese of fatigue? Yes, you're right. So we call this behavior fatigue. So if a material is under dynamic loading, we have to worry about a drop of the strength. And that phenomenon is called fatigue. And fatigue, the effect of fatigue depends on how many times of the load cycle that you apply to the material. Okay? So, is it okay? Okay, so, oh, there's someone taking a picture. Okay, thank you. Now, we can move on to talk about static loading. Okay? So for different kinds of material, we should use different models. Okay, and what are the difference between them? Some materials, some models, they're models. Those are math models. Okay. Some are more conservative. Some are less conservative. Okay? If you have a more conservative model, that means you want to be safe. Because maybe that material can fail easily. You want to design with greater safety. So if you use a more conservative model, your design will be safer. Okay, because you want to, conservative means you want to be safe. Okay, if you have a safer design, what will happen? Usually, safer design are thicker, stronger, or heavier. If you have a really huge table, you won't crash it, but it's very heavy, right? It's thicker, stronger, not strongest, stronger, heavier. So, what's wrong with this? Safe is good. What's wrong with it? More expensive and too heavy. Right? So you want to find the balance. You want to find the lightest design. And you want to find the cheapest design. But they are not safe. So the models are there for you to decide what's the dimension, how thick this table should be, what would be the proper diameter of the cylinder, so that this could be as light as possible, as cheap as possible, but still safe, under the low condition based on your application. Okay? So, so this is a guideline. This is a design guideline. You need to think about what kind of material you are choosing. So the first thing that you do is to decide whether you have ductile material or brittle material. So what are they? Ductile material means is more like a flexible kind of material. Chinese meaning is, did I write this right? Okay. Did I use the right word? 有写错字吗? Okay, good. Because I went to USA for 7 years. I didn't write any Chinese words for 7 years. After I came back to Taiwan, I forget so many Chinese words. Sometimes I look at this, is this the right one? Okay. Even I came back to Taiwan and then teach for 10 years. I didn't go back to high school and get my memories of Chinese words back. So sometimes oh my God, how do I write this word? Or how do I pronounce this word? Yes. Totally forget about Chinese. Okay, anyway, so for ductile material, it's more flexible. Okay. I should not say it's flexible. I should say it has the flexibility to deform before failure. So has the flexibility, or you can call elasticity to deform before failing. Okay, so it's elastic, more like a rubber, like a spring. If you deform and you release the load, it go back. That's ductile. But on the other side, brittle is like you can apply force, but when the force is too large, it breaks directly. You have little chance to see it become elastic. So in that sense, it's less flexible, like glass, like glass. Glass is a brittle material. So you never see glass being stretched, right? only when it's very hot. Glass material, it becomes more flexible when it's very hot. Otherwise, in room temperature, it's very brittle. So if you apply a force, if a brittle material can hold it, it holds it. But if it's greater than, if the load is greater than its strength, it breaks directly. You don't see it stretching. Okay? So how do we have a guideline to decide whether it's ductile or brittle? We check the strain. Okay? Strain for failure. Strain means how much you deform, right? Strain is deformation over its original length, right? So this is like a percentage of deformation. And this is strain of failure. How much strain you will have when it's about to fail. And if it's greater than 5, this is basically 5%. If a material can stretch greater than 5% before failing, it's rubber-like. If it doesn't deform, if it breaks and the deformation is smaller than 5%, it's like glass, it's brittle. So we use this as a general comparison or guideline to decide whether a material is ductile or brittle. Okay? So usually we separate them in this way. Let's talk about brittle first. Then you need to check your application. Can you be conservative or not? If you cannot be conservative, you have to be, I mean, if you decide to be conservative, then you can use this brittle Coulomb-Moore model. But if you decide not to be conservative, you want to be aggressive. Okay, the opposite of conservative is aggressive. Right? You want to be aggressive, then you can use this modified Moore model. Okay, and they can be found in our textbook. I put reference over there. If you want to read more, you can check our textbook. But for us, we are designing metal. Metal is ductile material. So I want to focus on the bottom part. The upper part, I don't care. I'm not going to spend time on the upper part. Only if you are interested, you can go to check your textbook. In the future, when you are working in a company and maybe you are designing a brittle material, make sure you cannot use those models. You need to use brittle material models. Okay? So today we focus on ductile material. Now there are this should be lower. Should be lower. Yeah. So what does that mean? What is this check? S is basically also stress. Okay. Sometimes we use this. Sometimes sigma. Sometimes S. Okay. So what does SYT mean? Y is yielding, T is tensile. So this is tensile yielding strength, and YC is compression yielding strength. So we don't like to study materials which has different yielding strength on tensile and compression. Like what I showed you earlier, if this is a material that has different values for both, then when this cross is on the top and I have force like this, it's under tensile, then how this material can handle this tensile stress is based on its tensile yielding strength. But when you rotate the cylinder and move the cross to the bottom, it's under compression mode. So for compression, you need to check its compression yielding strength. If they are not the same, we have to solve the problem twice. It's troublesome for teaching. So you need to know when you see a special case, when you have material has different strength for tensile and compression, you need to go this way. You need to use a different model. Okay? But for us, we assume all the material we consider has the same tensile yielding strength and compression yielding strength, so we can go this way. So whenever we do study, especially in a cylinder, when we analyze the stress from the top, the amount of stress you have will be the same when it rotates to the bottom. Because for stress of a cylinder, remember we have this model. Right, we have this model, and for cylinder, it's going to be 32 and pi d cubed. So this value will be the same when it's tensile at the top or compression at the bottom, same value. So for convenient, we assume these two are the same, okay? And I should say this is the same. Of course, I mean their limit will be the same. But we wish this to be smaller than our yielding strength, right? But the limit will be the same when it's tensile, and also the same when it's compression. The limit is the same, okay? That's the main purpose why we focus on the bottom. Okay, so for this very usual case, we have two models, and one is conservative, one is not. Maximum shear stress is the model we are going to introduce today. It's the most conservative model, most conservative. Okay? And if you don't want to be conservative, you can use maximum distortion energy model. And like I said last time, this is related to von Mises stress. Okay? And in many software, they use von Mises stress a lot. And you need to know, when you use a software and you decide to use von Mises stress, you are actually being less conservative, because you are less conservative if you use the model. Okay? So you need to know that. Like this slide can be done in 10 minutes, but you will miss a lot of key ideas. Now, let's talk about maximum shear stress model. This is the most conservative model for ductile materials, right? And for us, because we only want to deal with simple math problems, simple solid mechanics problems. So we only focus on plane stress or plane strain problems, which means no stress or strain on third direction. Or you can say sigma 3 or sigma z is 0, or strain 3 or strain z is 0. Okay? We just focus on 2D problem. Okay, for plane stress or plane strain. Do you still remember which one is which? Let me draw a huge material, and if I make a cut inside, and it's under some kind of low condition in the plane, okay? And if I make another cut somewhere next to it, another cut, the low condition of this cut is exactly the same as the cut next to it. What is this one? Plane stress or plane strain? Anyone remember? Anyone remember this? If I have, for example, this guy, if I apply a force and then if I make a tiny cut at the middle and I take it out, it's like a disc. So that disc is under some kind of low condition. And then I take the other cut just next to it. I take it out and take a look. Okay, these two cuts are under exactly same low condition. It's considered as one of the problem, plane stress or plane strain. Anyone knows? It's a 50-50 guess, right? Who thinks it's a plane stress problem? Just no punishment, just random guess. Plane stress? Okay, one. How about who thinks it's a plane strain problem? Okay. More votes. Good. It's the plane strain problem. So how do I memorize this? The reason why these two are exactly the same is because those cuts are stacked inside a huge material. They are being squeezed within this huge material. There cannot have deformation along this direction. I'm pushing you, you're pushing me. Because we're all squeezed in this huge material, we cannot deform in this way. Since we cannot deform along this direction, we have no deformation, no strain. So people call this kind of problem plane strain problem because the strain along this direction is zero. So here, if this is the third direction, strain third is zero. They call this a plane strain problem. If the coordinate system is like this is the 1, 2, and 3, there cannot be any movement along the third direction or the z direction. So in this assumption, there's no movement. The strain can only be zero. Okay, that's called a plane strain problem. So how about plane stress? For plane stress, it's basically a plate. Basically a plate, and you apply zero stress along third direction. So here's your 1, 2, and third, first, second, and third direction. Then for this kind, you truly apply zero stress along this direction, then it's a plane stress problem. Okay? I wish you can go back to find your textbook and check them again. Okay? Anyway, we are focusing on either a problem like this or this, and we only need to worry about a 2D problem. Now, recalling what we taught last time when we introduced the Moore circle, this is a Moore circle for pure tensile test. Like, let me recall your memory. If I have a material which is under a pure tensile force, then if we study basically a tensile test, and if we study the Mohr circle, you will see the Mohr circle look like this. Because if you treat this like a 2D problem, then you will have stress here. And if you study this point, here is only stress, no shear. So definitely you will have a point right here. You have sigma 0 tau. If you rotate 90 degrees right here, you have 0 sigma and 0 tau. That will be the origin of this point, of this diagram. If you rotate again by 90 degrees, you have sigma and 0 tau. You get back to here. If you rotate again by 90 degrees, you go to here. It's again 0 sigma, 0 tau. So it's the origin. That's how you form a circle, right? So for tensile test, the Mohr circle looks like this all the time. Okay? And we said when the material is about to yield, which means you are pulling this, when this pulling stress is reaching sigma yp or sigma y. So when this equals to sigma y, when this could be increasing its size when you increase the magnitude of your load until it reaches this point and your largest stress equals to your sigma yp or sigma y, the material is about to yield. Okay, so the largest allowable stress is under this condition. The largest allowable shear stress is under this condition, and at this condition, this point is having the largest shear stress. So for this material, the largest shear stress this material can handle can be calculated in this way. And from this diagram, you realize it's actually half of your yield strength. Half of your yield strength. Okay, so we can have a model, which means whenever we have a design, so if this is a variable, or I should not say variable, let's say this varies based on your design. And let's say you have larger loads, you have different shapes or different materials. So when I say, when this varies based on your design, what caused the change of your sigma, or of your tau max? Basically, the material you choose. But actually, when you say material, actually is more about it's not about material. It's about the load that you carry, and also the geometry of your design. Actually, that's it. Because if you take a look at tau, sin t pi d cube, t is how much load you have. It's a torque, twisting torque. And d is about geometry, right? So how much shear you may have depends on how much load and what's your shape of your design. Depends on those two factors. And no matter how you design your component, you design this to have this shape and also design this to carry some load. after calculation, you need to determine what will be the maximum shear stress for your design. Then you will check whether it will be smaller than the limit of your material. So this is like a limit of your design. And this limit, based on what we described, the limit will be half of your yielding strength. Okay, so this is related to material property. Okay, so in most design, if you have different load conditions or different geometry, what will happen is you will change the stress distribution in your design. You can change it, it's fine, as long as it is not too large. So the limit will be what kind of material you choose. Okay, so usually for any model, on the left-hand side, it's some kind of equation to calculate stress. And usually it depends on the load condition and the geometry. Once you have it, that stress should be smaller than some kind of limit. And usually the limit depends on your material. Okay, I think that's very important design concept you should have. For a general case, this is a general case. In the previous slide, it was a case for tensile test. Previous slide, this is for tensile test. For a general case, your Mohr circle may look like this. So this is a under general loading condition in a plane stress or strain problem. Okay, so more general. So in this general case, your principal stress you may have two different values for your principal stress, and they may not be zero. So in this case, you have a positive first principal stress, and you have a negative second principal stress in this particular case. So if you want to follow what we introduced earlier, you need to draw your Mohr circle and determine what is the magnitude of tau max. And based on our idea, tau max should be smaller than half of your yielding strength. This concept is always there. Okay, your tau max cannot be larger than half of your yield strength. So this is basically the calculation of your tau max based on this particular Mohr circle. So for a general case, you draw a Mohr circle, and then you can use this equation, or just calculate by yourself when you draw it. Then once you have that tau max, you will check whether it's smaller than or equals to half of your yield strength. If yes, it's safe. So if you get yes, your tau max is smaller than or equals to half of your yield strength. If yes, that means you have a safe design. Safe design. Okay. Otherwise, it's not safe. So what happens if it's not safe? It will yield. Because this equation came from the limit of yielding. If you satisfy it's within the safe region of yielding. If not, it will yield. Or even worse. Maybe directly break. Okay? So, should be very simple. Anyone needs a picture? Okay, good. Now, things are getting more complicated. Since we realize there's an equation like this for general cases, we would like to study this in several different ways. So remember, our third principal stress is always 0 because this is a plane problem. And in this particular case, two of your principal stresses, they are both positive. But because there's no stress on the third direction, so if you draw it, if you still plot it out in this Moore diagram, this is what you usually don't draw. So usually for this 2D Moore diagram, you only draw this. Okay? But my drawing right here is just to show you what happened if you consider this as a 3D problem. The third direction has no stress, and if you still plot it out right here, this circle, this one, is representing the 2D stress problem on the 1 and 2 direction. This one, the smallest one, represents the stress condition on the 2-3 plane. The biggest one represents the stress condition on the 1-3 plane. So in fact, on the 1 and 3 plane, there's a greater shape of your Moore circle. Even when we treat this as a 2D problem, there is still stress somewhere. And it's having a greater stress circle, a Moore circle. What does that mean? That means greater shear stress. So if you only focus on 1-2 plane, for example, this is the material we are talking about, and if we say this is 1, 2, and 3, if we only focus on the 1 and 2 plane, then it's like we're staying on this plane. We only study on this 1 and 2 plane. But in fact, even it's a 2-plane problem, on the 1 and 3 plane, this guy, on the 1 and 3 plane, there are some greater stress, greater shear. Greater shear stress on 1 and 3 plane. So when we design this, we simplify it to a 2D problem just for simpler analysis. But we cannot just ignore what's happening on the third direction. So when we use this maximum shear stress model, we try to also focus on what's happening on the other planes. So let's talk about what happened. So in the first case, when we have, so we're going to talk about cases one by one. But be aware, in this discussion, there could be discussions about the third stress, even when it's 0. Okay, so let's get back to here. In this particular drawing, in this particular case, when S1 and S2, they are both positive, in this particular case, our maximum shear should be the tip at the top of this largest Mohr circle. So that's why we should have S1 minus S3 in this case, not S1 minus S2, correct? If we are doing that, S3 is 0. So this equation reduced to S1 over 2 smaller than sigma y. And of course, we can reduce it to S1 must be smaller than S1. Okay. This is why we reduce to these two. But what's the difference between these two? Why do we say SA and B? Okay, so 1, 2, 3 represent the order of the magnitude, or should I say amplitude, magnitude of principal stresses. Okay? So usually we use 1, 2, 3 to represent the largest, the second one, or the 0 one. But what does AB mean? AB or even C? In this case, in my slide, ABC will represent the coordinate system or coordinate index. So in some case, or maybe you can change it to X, Y, and Z. Maybe that's more familiar to you. Sorry. Someone thought I'm angry. Okay. So ABC, or you can write it as X, Y, Z, represent the coordinate index. Sometimes S1 is parallel to, if we rotate the observation coordinate ABC or XYZ to a particular direction where you have principal stress. Okay, so sometimes, in general, your A may not be 1. Your A may be 2. Okay, so this is a very complete discussion for all kinds of situations. Maybe in some case, your A coordinate is having the largest principal stress. In other case, your B coordinate is having the largest one. So either way, in this first case, S1 is SA. In the second case, S1 is SB. We still derive them. So we now have two different equations. SA should be smaller than SY, SB should be smaller than SY. This is just because when you consider all situations, the Mohr circle 1, 2, 3 doesn't represent coordinate of ABC or XYZ. They can be different. So these will be two possible cases for case 1. Is it clear? Maybe you would like to see what's going to happen later on, but this is only 1/3 of this discussion. There are 2 more slides combining all three, we will see something interesting. So please bear with me and let's see what will happen later on. This is a different case where S1 is positive, S2 is negative. Okay? In this case, the largest Mohr circle is on the 1-2 plane. So this is where you have your largest shear stress. Okay, if that's where you have your largest shear stress, in this case, your largest shear stress should be calculated by the difference between S1 and S2. Okay. So if that's the case, we still follow, we can reduce this to here. Okay, we have, in this particular case, we have S1 minus S2 must be smaller than S1. But like I said, S1 could be SA or S1 could be SB. So either way, we plug in SA and SB into this equation. So we end up with these two. This should be lowercase. Okay. There are two different cases, two different possible cases. Okay? So this is when you have positive first principal stress and negative second principal stress. And when your first coordinate has the largest, this is the limit. When the second coordinate has the largest stress, this will be the limit. Okay, so we're discussing all kinds of situations. Is it okay? I'm moving on. Okay? Okay. Now, let me move on to the third one. The third situation is similar to the first one. The third situation is where both of your S1 and S2, they are negative, both negative. In this case, when we discuss where our maximum stress is, we will focus on the 2-3 plane. The Mohr circle on the 2-3 plane. And the maximum shear stress should be calculated by this. And because S3 is 0, so we reduce the equation to this guy. Negative S2 must be smaller than or equals to S1. And similarly, your SA could be your S2. Or the other case, SB could be your S2. So again, we are trying to discuss all situations. Okay, now we have described all possible situations, and we end up with 6 different equations. We will look at those 6 equations at the same time. So are you okay? Okay, now let's talk about those 6 equations, because those 6 equations are the design equations based on this complete analysis. Those are the 6 ones. All possible situations are here. And we use this SA and SB. So SA and SB are like the two SA and SB are the 2 principal stresses on AB plane if you use the coordinate index A and B. So let's say we have a material, and then if we orient it to the principal stress coordinate. If we do that, And let's say here is A, B, and C. I don't like this pen. Last one. I hope. No, it's not very clear. Let's recycle. Start from the first one. Okay. Okay, better, clear, better, more ink. Okay, so we orient this material to the principal stress coordinate. And we focus on plane stress problem, or just planar problem, right? Planar problem. So we only have, here is sigma C will be 0, and we have sigma A and sigma B. Only sigma A and B. But the A and B could be having the principal stress, the larger one, could be this one or this one. This is a general discussion. It doesn't guarantee this one should be the largest or this one. It could be any orientation, right? So based on what our previous complete discussion, in all situations, this SN and SB must follow all these 6 in general, because these are the 6 guidelines based on that complete analysis. So if that's the case, let's try to plot out these 6 linear equations in a diagram. So when we plot out this diagram, we are treating SA and SB as the coordinate axes. So I'm having SA and SB right here. Let's focus on how this SN and SB look like in a diagram. And they are inequality equations. Inequality. They are inequality equations. So when you see inequality equations that represent one side is not good, the other side is good, right? So let's take a look at the first one. SA must be smaller than SY. So SA right here must be smaller than SY. If this is SY, so this hatch is bad. This side is good. Okay, so when you see this, this is called hatch. Hatch is like, what's the Chinese of hatch? I don't know. 斜线阴影. Anyway, when you see this, those patterns, this is treat this like a wall. This is like a wall, and this is where you cannot go. You cannot go inside the wall, and this is where you can go. Okay, your design cannot pass through the wall. Treat this like a wall. Okay, and this equation basically is this boundary. Over here is bad, over here is good. Okay? Because if you follow, it will be safe. If you don't follow, it will yield. So let's follow this. Now the second one is SB smaller than SY. That would be this equation on the top. This side is bad. The bottom side is good. Okay? The third equation is a linear equation. This one is greater than. So this one should be this one. How do I know? If you plug in 0, 0, if you plug in 0 and 0 into this equation, it's definitely smaller than this. So that means this side is good, this side is bad. Okay? And the other equation right here is this one. And similarly, this side is good, this side is bad. Okay? And we did the same thing for these two. At the end, we have this nice figure. This, I don't even know how to call this. How do you call a shape with 6 edges? Hexagon? Hexagon? Okay. So hexagonal shape, right? Yes. So it ends up with this nice and beautiful diamond-like hexagonal shape. Is it? Like a tilted shape. So what does it mean? It means if you follow the maximum shear stress model, and if it's a plane stress problem or plane strain problem, then no matter what stress you have, whenever you orient that stress to principal stress coordinate, then the SA and SB must stay inside this hexagonal shape. If it's inside the shape, I guarantee you it's safe. No matter what orientation you are talking about, let's say if we are having a design right here, that means you have positive SA, you have positive SB, and it's within this region, no yielding. And maybe we have another design right here, and I have negative SA, positive SB. What does negative SA mean? That means in this particular design, along this SA direction, it's having negative stress. Along the SB direction, positive stress. But because it's within this hexagonal shape, it will not yield. But if one day we have a design like right here, I have positive SA, negative SB, but it's over the boundary, it will yield. It will yield if that's the case. Okay, so this is the maximum shear stress model. Okay? Always check your Moore circle first. No matter your SA and SB is in which condition, if it's inside this hexagonal shape, then you're okay. Usually I don't try to memorize those. I just draw this drawing, make this drawing. So how do we get this drawing? It's very simple. This is SA and SB. And then draw 4 dots. This is sigma y or sy. Sy. Here basically negative sy, negative sy. And then make a drawing like this. That's your boundary that has a hexagonal shape. Very simple. Once you can memorize this, you don't need a math. That's your equation. Okay, and then later on, you just plot a design point here, plot it in, and see if it's safe or not. So for our homework, we can already use it. For our homework. So let's get back to our homework. So for the homework, remember we have a problem like this. Maybe that's the stress. It's a plane stress problem, right? Plane stress. And then we will draw a Moore circle, maybe something like this, right? And you have your S1 and S2. So this is positive, this is negative. So if you plug into this maximum shear stress model, if you plug in these two numbers, it will be somewhere positive and negative, maybe somewhere here. Somewhere there. As long as that point is within this region, then it satisfies the maximum stress model. Okay? Or if you decide not to use this, you can of course calculate the maximum shear stress and then use this. You can use this. It still gives you the same guideline. Why? Because all these equations came from this. You can either use it directly by calculating the maximum shear stress, or you can use this guideline. This has a Ghana guideline. They're the same thing. Okay? So later on, when I ask you to do a homework, you will be repeating what you did for the first homework. And then you will try to use a model to check whether it's safe. And I can also let you know how safe it is. So how do we, this is about how safe it is. So what does that mean? Previously, I have a greater shape, greater boundary. Now I want my design to be safer, so I decided to apply a safety factor on the right-hand side of my equation at the bottom. Okay? If I do that, this upper limit becomes smaller because n is greater than 1. Usually we have design with n greater than 1. What is n? Safety factor. Because n is greater than 1, this upper limit for every equation becomes smaller. If the upper limit becomes smaller, we have a smaller design region. When we have a smaller design region, what does that mean? That means we can only allow, let's say, we have, let's take this as an example. Basically stress, right? If this whole number drops, that means the stress I can carry drops. I can only handle lower amount of stress. If I have to handle lower amount of stress, that means I need to reduce load or make geometry thicker or larger, right? If I have a design equation that is safer, when I put a safety number here, the limit becomes smaller. So the stress has to be smaller. If I want the stress of this cylinder to be smaller, I need to reduce the force. Or I make it thicker, stronger, bigger. So this is how you can have a safer design than the original. In the previous slide, if I don't have a safety factor, my design region is larger, I can carry greater loads, I can have smaller design, but it's more dangerous. What if you are reaching the limit, and if you are not lucky, one day the load get out of the boundary, then your material breaks or yield. So we want to be safe. We shrink our design region. we don't allow ourselves to design close to the boundary. Too dangerous. Okay? So take the elevator as an example. Whenever you take an elevator, knowing we'll take an elevator. Usually we'll tell you it allows 10 people in there, right? Elevator. Usually there are cables, maybe a lot of cables. What will happen if I have another people come in, 11 or 12, 13? I think we can actually put 20 people in there. It won't break right away, but it's very dangerous. So usually when it says, please only have 10 people in there, it's like this boundary is where you have 10 people. Oh, by the way, PPL is people. PPL is people. When you have, usually for a design like this, it's having a greater safety factor. So let's say if you follow its maximum limit and put 10 people in there, you are maybe reaching the limit on the red boundary. But there's a long gap. There's a huge gap. Maybe the elevator can truly handle 20 people. Maybe. But it only allows you to have 10. Or maybe 30, who knows? We don't want to try it, because if we try it, someone will die. Not more than one people can die. So the number of safety factor really depends on applications. Whenever it's application about human life, it's having a very large safety factor. If it's not, like this table, maybe one day a heavy person sit on the table and this bended, that's fine. Let me buy another one. That person won't die. Maybe just fall onto the ground and just get hurt a little bit, but it's not about his life. Then I don't need to have the strongest table right here. It will be too expensive, waste of money, too heavy. Okay? So that's the idea of safety factor. Now, let's try to apply this idea to a problem, and this is actually the exact problem that we had last time, and actually exact problem for your homework. But the number is different. I pick up some number from my previous slide. And I bring this just to show you what happened. Last time, I tried to follow this. So over here, this is where we have our pulley, another pulley. And I remember we have pulling up right here, right? We pull up. And here we pull forward, I think. Pull forward. I'm not sure if you can see it. This is pulling up, here is pulling forward. So if this pulls up, this bends like this. And this pull forward, so this bends forward. So this is bending up, this is bending forward. So it's really complex when these two bending mix together. Okay, so after our calculation, we realize at some point right here, somewhere right here, it has some some bending toward that way, some bending toward up. So it's going some bending toward this way, some bending toward that way. So it actually bends in this direction. So if it bends in this direction, the maximum tension happens somewhere here at the bottom, at the back. So we have some bending. We have some bending in this way, and I think we have some bending. Do we have some bending in this way? Based on my drawing, I think that's what I meant. So basically, it was not pure bending along this way, not pure bending along this way. It's like a complex, a combination of both effect, and it bends along the other way. So on one of the angle, that's where you have the largest bending. And at the top of that orientation, where you have the largest bending, at the tip of the point, you visualize it on the top, you see this. That's where you have the largest bending and largest tensile. Okay, so that was what happened when we try to study at this point. Okay, anyway. So I'm not sure if you can visualize this better. That's why I try to draw this. Anyway, on that particular point, that's where we have our low condition, and we draw this Mohr circle. And in this case, we have our S1 right here. It's positive, and S2 right here is negative. Okay, so it's one of the situations that we introduced earlier. And the easiest way, one of the ways to do it is just calculate the maximum shear, and that's what we did. And we said as long as it's smaller than the yielding strength over your safety factor, then you're fine. Okay, so I use this, and I think I try to assume this material as steel. So if this is steel, steel has 350 megapascal of yield strength. So let's consider some steel has 350 megapascal yield strength. In that case, under the low condition that I had earlier, at the end, we end up with an equation like this, and we realize, okay, n is smaller than 13.89. So what does that mean? That means this is the safety level. This material has. When it's under when it's under the specified low condition. Oh, sorry. Okay, so when it's under this low condition, this shaft actually has this safety level, 13.98. It's a very large number. I just randomly pick up some material number, randomly pick up some material property. So you usually don't have a design with this large number. It's too safe. But what if we have 3D printing for this? PLA is a very popular 3D printing material, and typical yield strength is around 26 megapascal. You can see the safety level greatly reduced to around 1. Still larger than 1, but greatly reduced because metal has 13 times greater of yield strength. Okay, so this is just for you to to realize, oh, if you use metal, it's 13 times stronger. If you use plastic, it's 13 times weaker. Okay? Just for you to have a sense of it. Okay. What's this? This is also very important. And this is where you may want to memorize stuff. Okay. Very important slide, because for future problem solving, you may use this for many times. This is a problem this kind of law diagram is the diagram that we use a lot for shift. This is a shift or a cylinder with bending plus twisting. So usually if you have bending and twisting on a shaft, your loading diagram looks like this. Sometimes the shear stress goes the other way. Sometimes the tensile stress goes inside. But usually it looks like that. And if you draw the Moore diagram and then try to formulate the maximum shear stress over here, this will be the equation. This is the equation. Sigma squared over 4 plus tau squared, and then take a square root. This is the equation. And we use this equation a lot. Okay? So please keep in mind, you have an equation like this. Later on, when we introduce different models, we will bring this back and we will compare what happened. The equation, we will see similar equations, but slightly different. Okay? And if we apply these two, remember we based on the solid mechanics, we have sigma equals to 32m over pi d cubed. And we also have tau equals to 16t, basically torque, over pi d cubed. This is moment, this is torque. If we put them in, it ends up with something really messy. Okay? But if we have something like this, what can we do? We can make very good use of it, because if we pick up a material, this was PLA, right? And remember, in the earlier example, when we used PLA, the safety factor was close to 1. If I want this to be safer, if I choose 3, how can I make it safer? So if I pick up the decided material and also decided safety level, I want the safety level to be 3. Then, under the same loading condition, those are the moment and torque that we had earlier. What's left would be the diameter of the shaft. So at the end, in this equation, we end up with unknown parameters d. And this is something we can use to determine how thick this shaft should be, so that we can reach a safety level of 3. Okay, so at the end, d must be greater than 49.9. So in the previous example, I think the diameter was not 49.9. It was smaller. I don't remember the number, maybe 30 or 40, but it was thinner. So if I want to reach certain level of safety, I can use the equation to determine what's the exact diameter to use to manufacture this, so I can reach the exact safety level. Okay, so this is also known as reliability engineering. Reliability and engineering. Basically, design of mechanical components or mechanical design is a reliability engineering problem. Okay? So, when we solve a problem in the future, I may give you the dimension, or I may give you the material property, or I may give you safety level. In this equation, we have several unknown parameters. This is about material. This is about safety level. And D is about dimension. How much load we have, what's the geometry, what kind of material we choose, what's the safety level. Always 4 factors. We need to consider all 4. So usually when I give you a problem, I tell you 3 out of 4, you can calculate the unknown. If I tell you dimension, material, and I want to reach some level, you can tell me how much load you can carry. If I tell you I want to carry some load, I have some dimension, I pick up some material, you can tell me how safe the design is. Okay, and there are many combinations of this possible problem that are given. And in reality, when you go to a company and you are designing for a component, it's always like that. Load, dimension, or geometry, material you choose, how safe it is. And usually, for engineers in the industry, they sometimes cannot figure out the safety. So sometimes the design is too safe, then the company will lose money because it's too big. Sometimes the design is not safe enough. The company also lose money because a lot of complaints from the customer. So reliability engineering is the key to make money for a company. Important. If you can properly design the level of safety, you not only can maintain safety and cost. You can find a balance between safety and cost. Okay? And also performance.